Okay, we can start. So today we will start with systems with damping. Systems with damping. In many practical problems, there are many sources of dissipation, and analytical and precise models are difficult or impossible to develop. Therefore, in the most cases, one introduces in the system an artificial dissipation model that allows to replicate as well as possible experimental data when they are available. Therefore, now we see we are going to consider the effect of dissipation in the vibration behavior of any degree of freedom systems through the viscous damping model. So we start with a generic system. M Q double dot C Q dot plus K times Q equal forcing. The objective is the decoupling of the mass and stiffness matrix. It's quite obvious. Therefore, the system can be decoupled if U, C, and U is diagonal. This is a primary condition for decoupling, but only in special cases. But now I would like to start the study of damping from these assumptions. We will start with generic viscous damping. So let's start. 2.6.2 generic viscous damping. For a generic system, the damping matrix 6C cannot be diagonalized by the modes of the undamped system. In other words, the presence of the dissipation changes both the eigenvalues and the eigenvectors, which are in general complex. Therefore, the new theory must be developed for analyzing the most general case of viscously damped dynamic system, which is generic viscous damping. In order to generalize the model analysis to generically damped systems, we have to work in the phase space, which is the phase space. It is Q dot Q. So this is the phase space. In particular, we also use the Duncan approach. Okay. The initial ODEs is joined with an identically satisfied ODEs, which are these ones. So we have MQ dot minus MQ dot equals 0, and we have also our system MQ double dot plus CQ dot plus QK Q forcing. And now we have the vectorial form of this. I think is okay. It's better now. Okay, the vectorial form. So we have a mass matrix, which is not a mass matrix. We have a first matrix. We have M, 0, no, M. First here is 0. 0, M, M, C. Times the vector Q dot, Q double, no, Q double dot, Q dot. Done. Yes, done. Plus another matrix. This is basically this equation, this system of equation in the matricial form. M 0 0 K and another matrix times the matrix Q dot Q, which is equal to 0 F. Done. This is the matricial form, and then we can consider a more compact form. A times y dot plus by equal G, where y is a matrix, is a vector Q dot Q. This T is that it is a transpose. So these are the governing equations in the steady space, also called phase space, state space, state. So we have here our phase or state space. Similarly to what was done for undamped systems, let's us start with the analysis of the autonomous systems. In other words, free vibration problem. So consider a free vibration problem. What defines a free vibration problem? AY dot plus B y equals 0. The solution can be written in the general form. So the solution for the general solution for a system like this is y equal to V times epsilon lambda t. Okay, let's do it. Let's move forward, and then we will use we will try now to reach the eigenvalue problem. For that, we will use two equations. We will use these two that I just wrote. We will use these two to reach the eigenvalue problem. So the eigenvalue problem is minus omega lambda times A plus B times V. This is equal to 0. The characteristic of, this is the eigenvalue problem. Okay. The characteristic equation is a polynomial of degree 2n. So we will try to which is the characteristic equation? Is the determinant of the eigenvalue problem. not the eigenvalue problem, the determinant of the what is inside the parentheses. So the determinant of lambda A plus B equal to 0. It furnishes 2n complex conjugates eigenvalue and 2n complex conjugates eigenvector. So this is the characteristic equation. Consider now equation the eigenvalue problem. Now let's write again the eigenvalue problem. Consider the eigenvalue problem for a pair of lambda y, lambda I, and vi. And then I will consider that and left multiply by the eigenvector vj. So vj. Okay, so we will finish with a system. Lambda I vj transpose times A times vi plus vj transpose times b times vi. This is equal to 0. And then lambda j lambda j times vi t a vj plus vi t b vj. This is equal to 0. Now we have a system, and then we will take advantage of the symmetry between A and B. So considering the symmetry of A and B, okay, we will have now Vj transpose times A times Vi. AI, this I is similar to J, so AI delta J, and then Vj T times B times Vi equal minus AI times lambda I times Ij, and then we have another system. But what is this? This will be a modal matrix we can create a modal matrix. From this, we can create a modal matrix V, which is equal to V1, V2, until V2n. This is modal matrix. Then, applying the orthogonality conditions, we will have Vt, which is the vector now, times A times V. Remember in the beginning when I told I told about the diagonal, so diagonal of A I and Vt times B times V, which is equal to the diagonal minus lambda I times AI. Yes. Hence, the projection of the modal space is equal to V times neta this is the model, the projection of the modal space. Using the orthogonality conditions again, the initial equations are decoupled. So neta dot lambda I times neta I. This is a first order solution, the first order equation, and the solution will be Ni times Ni0, which is initial condition, times epsilon, okay, exponential of lambda I times t. So the initial conditions are now projected on the modal space as well. Okay, but which are the physical meaning of the eigenvectors? Of complex eigenvectors. So Just check first stuff. The damping changes the nature of the eigenvalue problem associated to the free vibration of a mechanical system. Without damping, it has in real eigenvalues and eigenvectors. With damping 1, the system will have 2n pairs of complex conjugate eigenvectors and eigenvalues. So, in the case of absence of damping, the eigenvectors represents the amplitude of the synchronous motion, so with no damping. The question is, what is the physical meaning of the eigenvector? There is no physical meaning, straightforward saying. Its component cannot represent amplitudes as they are complex. However, we have to point out that any complex eigenvalues or eigenvector is always associated with its complex conjugate. If a mode exists, its complex conjugate exists as well. Let us consider some such pairs in terms of real and imaginary part. So, just to check something very important here. Okay, lambda I is lambda I real plus j lambda imaginary also I. Lambda I okay is equal to lambda I real minus j okay minus j lambda I imaginary. Okay, and v I equal vi r plus j vi I. Same thing, but just check something. Translate. Okay, it's correct. 27. Nice. Okay, so vi asterisk equal vi real minus j vi I. The real vibration associated with a single complex mode of vibration is y I equal vi times exponential of lambda I times t plus vi asterisk plus exponential lambda I asterisk time t. This is equal to 2 times the real of vy times exponential lambda I t, which is equal to 2 times epsilon I times lambda real I times t, and this is multiplying all this expression here, v I r times cosine lambda I t minus vi imaginary times sine of lambda imaginary I times t. Close parenthesis. This proves that the vibration associated to a complex mode is made of two real displacements, vectors, the real and imaginary parts of the complex eigenvector. These two vectors are associated with the same. Well, look at that. Okay. No, it's correct. These two vectors are associated with the same harmonic time story with frequency omega is, which is lambda equal to lambda imaginary of I, time shift equal to 1/4 of the period. Assuming that the system under investigation are passive, or dissipative, if the damping ratio is subcritical, so what we have is lambda I equal lambda R plus J lambda I imaginary, which is equal to minus omega I times, I don't remember this letter, so plus J times omega I, which is the damping. This is the damping ratio. Damping ratio, yes, damping ratio. I don't remember the name of this letter. It is a Greek letter. So the damping ratio, so square root of 1 minus the square value of the damping ratio of I component, just minus omega I times the damping ratio I component plus J times omega is. Finally, important to say the conditions here. Subcritical. Damping ratio. Dissipative system. Which is in this case is mq double dot plus c dot plus q is equal to 0. So in the end we will obtain what? We will obtain that omega of component I is equal to modulus of lambda of component I, and the damping ratio of component I, which is the negative of the real part of lambda I over the modulus of lambda I. This equation is valid for subcritical damping ratios, as I told you. For complex eigenvalues of equation 138, so equation so this is valid for this equation for lambda a plus b So this is the solution of the eigenvalue problem. It's valid for this eigenvalue problem. In fact, if an eigenvalue is real, the first equation does not return the frequency of oscillation, but simply the absolute value of the eigenvalue. And the second equation will return a positive or negative unitary value. So, therefore, the case of very high damping must be analyzed in a different way, which is not will be discussed here. So damping should be subcritical, damping of ISO -1, and this is valid for, this is the final damping and the frequency, and the natural frequency of a dissipative system, and which assumes this eigenvalue problem. The structure of complex eigenvectors are given by Vi. We have lambda I times psi I and psi I, which is a vector. So this partitioning is showing that the information of a 2n dimensional vector V is contained in a n dimension vector psi. Contains n, and this is the generic viscous damping. Let's take a look in another subject. Let's check. Generic viscous damping, synchronous systems with damping. Let me check. Okay. Okay. Now, to finish this part, the forced problem. Okay, let's check. Once the modes are calculated, the analysis of the forced problem is almost trivial. we take advantage of the orthogonality conditions. So let's consider the orthogonality conditions. Consider the orthogonality conditions that we saw. Vt times A times V. This is equal to the diagonal of AI and the Vt times B times V, which is equal to the diagonal of lambda minus lambda of component I times A of component I. So this is the orthogonality conditions. Okay, so from this we have y, which is equal to v, the vector of v components, times neta. Then if we and applying this on the orthogonality conditions, using the orthogonality conditions on y equal v times neta, we will have Vt times A times V times neta dot plus Vt times B times V times neta dot times neta without dot. So this is the V transpose times G, which is equal to P. In terms of components, we will have neta dot of component I is lambda I times neta I plus P over A, both of component I, which is equal to lambda I times neta I plus Pi. The solution then in time domain is the integral from 0 to t of epsilon lambda I t minus tau Pi tau d tau. Note that this solution has been obtained applying the convolution integral method to the first order systems. So nice. And this is the finish of the generic viscous damping. Let's close here. And see you in another topic.